I talked to different people here, and I realized that some people understood what I was talking about, and some people were absolutely clueless, and had no idea what I was talking about.
State of affairs.
Hmm?
That's the normal state.
It's the normal state of affair, but I wanted to take a small step to fixing that. So what I'm going to do is talk about one other topic, and then I'll let you ask questions at the most basic level about what I am up to, okay? So that we can get some sense of why we're doing these things, because I don't think, everyone understands what's going on with quantum computers running optimization algorithms, because it's a tricky subject, okay? We'll do our best. So anyway, I told you about some stuff. Can people hear me in the back? It's okay? The volume's okay? Thank you. So I told you about some stuff which I think is interesting. I'm going to tell you one other weird thing, and then we'll go to the attempt at satisfying everybody. So I have to go further up. I have all these talks. Oh, yeah, that was interesting. I didn't talk about that. That was interesting. Okay, I talked about that. See, the trouble, I'll tell you why I'm upset. You see that slide which has a mistake? I can't fix it. Because I just can't. It's impossible. Because the way I make the slides. So frustrating. Anyway, too bad. Okay, so anyway, here I'm going to talk about another topic, which is the QAOA gets stuck starting from a good classical string. And these are my collaborators, Maddie Kane, she's a graduate student at Harvard. Sam Gutman, who I work with on everything. I went to high school with him. Dan Renard and Eugene Tang, who are postdocs at MIT. And let me tell you what happens. So the usual QAOA starts in the uniform superposition of all inputs. And that's because we start in this state, which is plus in each direction. And, that's the uniform superposition over every possible string. And if you want to just see why that is, why that's an easy thing to make by going into the x basis, you notice that the plus state, plus means an eigenstate of sigma x with eigenvalue 1, is 1 over root 2, 0 plus 1. And if I multiply those out, so if I have 3 of them, I get 8 terms, which are 0, 0, 0, 0, 0, 1, etc. So by lining your spins up in the x direction, you're already starting in the uniform superposition of all possibilities. And that seems like a very natural place to start. Because, you're trying to find the optimum. Let's start in the uniform superposition. And that's the quantum analog of, let's say, starting an algorithm and just randomly flipping to produce a string, which is the starting point of your classical algorithm. But this is quantum, and this is one state representing them all. So, then we talk about how well the QAOA does. But now, you might imagine doing the following thing, which is run a classical algorithm and get a good string, which I'll call W, which is W1 to Wn. And the classical algorithm might be simulated annealing, which some people know what it is, some don't. But anyway, simulated annealing is a classical algorithm that's very successful for many combinatorial optimization problems. Now, of course, it's not provably successful in worst case. Otherwise, P would equal NP. So but still, it's very successful. But for MaxCut, there's another algorithm called Gomans-Williamson, which I think has been alluded to here. Gomans-Williamson is an algorithm for MaxCut, which gets a provable approximation ratio of 0.878. It's sort of fascinating that there is, I think I mentioned this before, but anyway, Gomans-Williamson gets 0.878 in worst case. I mean, in any instance, it would give 0.878 or better. And so, you could say, okay, let's run Gomez-Williamson, get a good cut for MaxCut, and then use that as the starting point. And then what we're going to do is we're going to define the QAOA unitary, which is that sequence of transformations. And we're going to now, instead of starting in the uniform superposition, we're going to start at the good spot. I mean, why not? And then vary the parameters to do better, because I want to optimize the cost function. And, if you look at what the cost function is, okay, we don't have these things. Oh, we do. We have a new box, okay. Because what we want to optimize is gamma, beta, I'll write it as U. W, U, dagger, gamma, beta, the cost function, U, gamma, beta, W, and see if the parameters are 0, these parameters are 0, you get the cost function of W. So you would think that by varying the parameters, you can only do better, because you're starting at the cost function of W. But what happens if you go to the computer is it doesn't work. You don't move at all. It's sort of remarkable. So for example, on even this computer, I toss a 16-bit 3-regular graph. So a 16-bit 3-regular graph, again, it means that every vertex has 3 friends. And it's just something to do, pick a 3-regular graph. You got to do something. But you see, on a 3-regular graph, it has 24 edges. That's just a simple calculation. A 3-regular 16-bit graph has 24 edges. So that means that if you take an average cut, you cut half the edges. In other words, if I randomly assign plus and minus 1s to the vertices, I cut half the edges. So the average cut is 12. And so 12 is where the usual QAOA would start, because it starts in the uniform superposition, so it starts at 12. So 12 is kind of a crappy cut. And a 3-regular graph like this, maybe it has a cut, the best cut is, 22. It's not going to be 24. 24 is too much. So maybe it's 22. So then I can just go to the computer and find a string whose cut value is 15. So now my classical algorithm for finding a good string is just look at the different strings and pick one with myself. But that's a classical algorithm. I pick one. And I pick one at 15. And then I start in W, where CW is 15, and I look at P equals 1, 2, 3 at higher and higher depth. And every time I attempt to optimize with numerically, it returns that the best parameters are 0. Just never moves. And sometimes it moves by a little bit, like 0.2. And this is very weird, because, to me anyway, and then you could say, well, maybe you picked a bad one, or a typical one. But at this number, I can go through every single string whose cut value is 15, because I have them in the computer. I go through every one, it happens every time. Or sometimes it may be improved by 0.2. But if I increase it to 17, let's say, nothing ever moves at all. So it's sort of unusual. Yes?
So, no computer if you start with the product string in the computational basis.
Yeah.
And then, so the first step of the algorithm is C++.
I'm sorry, if I start in the uniform superposition.
Some product state.
Well, that's a product state.
Yeah, like this one.
That's a product state.
Or the 0 product state.
Oh, which one?
Or just the uniform 0 product state.
The uniform 0? You mean?
The 0 bit string.
Just
or any product state.
Any product state
in the Z basis.
Oh, in the Z basis. Thank you. Yes.
And then, so your algorithm starts with a rotation around the pauses, and it does rotation, the next rotation, right? If I take the gamma of the first rotation,
Oh yeah, that doesn't do
first one
anything.
to 0.
The first one doesn't help because
Yeah.
that just introduces a phase. So that's not there.
So let's just take it to 0.
Yeah, the first guy, that's fair.
And then the second one, if I take that to pi over 2 or whatever, I get a uniform superposition, right?
Correct.
So, I mean, I'm kind of back to where I started.
Very good.
So I
Yeah.
can just increase p by 1 and get like the same behavior.
Great. Okay, that's
starting
it.
with that uniform superposition string.
Almost.
Almost?
No, you're almost right.
Okay.
Yeah. Yeah, well, what he said is quite true. What he said is this, is if I start in any string, if I start in any fixed string W, and it's actually, if I act with e to the minus I pi over 4 times the sum of the sigma x's, okay, if I do that, what I am going to get is 1 over the square root of 2 to the n, a superposition over all z, okay? But they're going to have funky phases, okay? But that is, there'll be a funky phase for each one, right? But that, if I take the expected value, if I take the expected value of the cost function in this state, it will be 12. It'll be the average, right? So if I do what you said, what I can do is I can take a bad string whose cut value is below 12, and I can rotate it to 12. That I can do. So I can take a bad string and make it mediocre, but a good string I cannot improve. Because now you're saying, oh, now I start the QAOA from here. It doesn't work. No, because there's a big difference between starting here and, yes, I mean, you're making a very good observation. You're saying, why can't I start here? But where we actually start is 1 over the square root of 2 to the n, the sum on z, with phase 1 for every one. Those are hugely different. But, you know, your observations are correct, but that's part of the weirdness here. You know, when I say we start in the uniform superposition, I have to start in the uniform superposition with phase 1. Otherwise, it doesn't work. Well, intuition? No. But I'm not a fan of intuition, you know. I'm a calculator. I don't, no, just kidding. No, I don't really. But let me keep going, and we'll see whether we make a tiny bit of progress on this. Okay? But it's very strange to me, because, I mean, suppose that you were doing, you know, like, for example, you know, suppose that you were running simulated annealing. Simulated annealing is an algorithm which starts with a crappy string, and then as time goes on, it produces a slightly better one, and a better one, and a better one, and a better one. So suppose, you know, you ran simulated annealing for a while, and you stopped. And you said, now I'm going to start again. From there, well, it would just go up. You know, but if you ran the QAOA, and you said, I'm going to run it for a while, and then I'm going to stop and measure a string, and then I start from that string, it's no good. Now you say, well, wait a second. Suppose I was going to run the QAOA at depth 4, and I stopped after 2 rounds. If I took that quantum state, I could keep going. Because, in other words, if I think of the QAOA as running a sequence of, let's say, at depth 4, let me think of it as 4 unitaries. Unitary 1, unitary 2, unitary 3, unitary 4. And I stop after unitary 2, and I just take the state, and then I do unitary 3 and 4. Well, I didn't do anything. But if I measure it after 2 rounds, and I get a string, then it won't move again. So there's something magic about the superposition, as opposed to being in individual strings. And those superpositions have funky phases. Okay? And I don't understand this. But I think it's fascinating because, it's hard, I don't know. It seems to me that most classical algorithms, it depends on what they are. The one I think about the most is simulated annealing. Maybe I should explain what that is if people don't know. But in simulated annealing, you start with a random string, and then you change a bit. Or there are things called like greedy algorithms or walk algorithms where you have a string, you start with a crappy one, you have random assignment of zeros and ones. Then you flip a bit. And you say, should I make the bit flip or not? Well, if the cost function improves, you do. And if the cost function doesn't, maybe you don't improve. So then you say, great, I made a little improvement, I'll go to another bit. I'll flip it, and if the cost function improves, I accept. And if it doesn't, I do another one. In simulated annealing, you sometimes accept a bad move because it doesn't always, you can make you will accept a move that brings down the cost function with a certain probability. And that probability actually puts you in the Boltzmann distribution. And that in simulated annealing. And so if you can enter the Boltzmann distribution at a low temperature, you'll have a low, it's very annoying because in optimization you like to go up, but when you talk about simulated annealing or physics, usually you want to go down because you talk about lowering your energy by being at a low temperature or finding the ground state. But here I need to go up, and the reason we go up in optimization is because I'm interested in something called the approximation ratio, which is the number of satisfied clauses divided by the maximum number. And if you did it in terms of unsatisfied, the denominator would be 0. So go ahead.
You know what would happen if you would initialize with superposition of like the Boltzmann distribution and
Oh, okay, that's another good question. Like, for example, I can go here, let's say not the Boltzmann distribution, but I start in the uniform superposition of every string whose cost value is 15. That's easy for me to do on my computer. Okay, you don't move. Yeah, another weird finding, numerical finding. Yeah, no, you don't move. You get stuck. I mean, again, I do this. I can verify this on the laptop. And I want to say another thing here about simulation, because sometimes people think, well, you can't learn anything at low bit number because anything you learn might change at high bit number. But this is a phenomenon that's very hard to believe that would change when you went to high bit number. Because if your algorithm is getting dead stuck at very low bit number, and even if you don't know why, it's hard to imagine that making it bigger will make it better. So I think the fact that this is dead stuck at low bit number is something which, and then I have arguments for this, but just in terms of the intuition you might develop from simulation, I think there are times when low bit number simulation can teach you something. And I think this is a case. So let's see if we can get a tiny intuition. Well, it's a slight intuition, but it's not great. So let's look at, I always talk about MaxCut. Someone asked me why MaxCut. Well, MaxCut is just the prototypical NP complete problem. It's very simple to state. You have a graph. I'll restate it. You have a graph, and on the graph, you assign bit values plus or minus 1 to every vertex, and you wish to find the assignment that maximizes the number of edges on which the 2 bits on that edge disagree. And that's a very simple problem to state, and it's completely generic. It's the prototypical, optimization problem, and I just stick with MaxCut because I just did. So let's remember the MaxCut cost function, which we discussed before. It's the sum on the edge is 1/2 1 minus the IZJ. And again, if the 2 bits agree, then you get a 0. And if the 2 bits disagree, you get a 1 for each clause. And that's the way we define it. So now let's look at an individual term. So I'm going to look at the expected value of one clause term. I look at the expected value of one clause term. Now notice that if u is 1, if I do nothing, if the bits in the string W, I, and J disagree, then this clause is satisfied and I get a 1. And if they agree, I get a 0. And if U is not, and so that's for a, the value of this at U equals 1 depends on the bits. If you either satisfy or you don't. But now suppose that, but these clause functions, they're between 0 and 1. So that means when U is not 1, this can only go down a little bit, and this can only go up, if at all. So suppose this goes down by an amount epsilon, if Wi is not equal to Wj, and this goes up by an amount delta. So one goes down and the other goes up. Okay? Now, suppose that the amount you go down is equal to the amount you go up. Just suppose that. Then you'll see that you can't make progress because in a good string, there are more satisfied edges than unsatisfied. And so all the satisfied edges go down by a certain amount. The unsatisfied ones go up by a certain amount. But there are more good ones who are going down than there are bad ones going up. So you cannot move if this is true. Okay? Does that make sense? Okay, good. So that's that law. So now let me show you an example where this actually happens. And here I'm going to take a decoupled graph. By a decoupled graph, I mean something where this is my graph. 1 is connected to 2, 3 is connected to 4, 5 is connected to 6. Now, this is a very easy problem to solve, right? Because if I want to do MaxCut, I make this a 1 and this a minus 1, this a 1, this a minus 1, this a 1, and this a minus 1. This is a very simple graph. But because it's so simple, I can analyze it. And actually, I can prove that for any QAOA unitary U, we can prove that epsilon equals delta. In other words, we can prove that no matter what the depth of the QAOA, how many rounds, because it's so simple here, it's only a 4-qubit. You're just analyzing a 4-qubit space. And it's very symmetric because it has a bit swap interchange. It has it's very simple. I mean, you can just do this with a piece of paper. I can analyze this little guy. And so you can just prove this. That's interesting because I've now proved that at any depth, so since I can do this, prove epsilon is delta, this proves that for this particular example, at any depth, if I warm start the QAOA, it will fail. So it's just nice to have an example. But I want to contrast that with the performance of the QAOA where the usual QAOA. And it turns out that the usual QAOA at p equals 1, starting in the uniform superposition, works perfectly. So in other words, I forgot, I have it written down somewhere, but I don't know, beta is like pi over 8 or something. I think beta is pi over 8, and gamma is like pi over 4. I don't remember. But you can just do it by hand, and you achieve perfection. So, it's sort of entertaining to me that here's an example where starting in the uniform superposition, you achieve perfection at p equals 1, and starting in a warm string, you only get failure. And of course, again, if you start in a bad string, I can bring it up to mediocre. I can bring it up here, I could get a cut fraction of a half if I started if I'm in a bad string, the cut is 0, but I can bring it up to expected value of a half. But I can, anyway, so why do I care about this? We have arguments, thermal arguments and stuff, for why this might be the case. But I think it's very interesting in a way because somehow or another, the QAOA, if you start, like we asked before, if you start in the uniform superposition of everything good, you don't move. But if you start in the uniform superposition of everything good and bad, you just make progress. And I want to say another thing about the QAOA. which is that every numerical experiment anyone has ever done, we're starting in the uniform superposition. As you increase the depth, you just get better and better. There's never been any evidence that the QAOA gets stuck. And, you know, Thomas Vidic would say, so, you know, who cares? You have to go to very high bit numbers where it will get stuck. But, you know, that can only tell you what I can do. So anyway. I'm sorry? Yeah, well, I'm not going to say that.
And you chose here MaxCut.
Yeah.
Why can't you choose something like a preset?
What? Okay.
And deliberately add clauses that contradict each other, which means that like the maximum will be lower than half, and then these perturbations will make you go up and not down like here. If it makes sense.
Not exactly. So you're saying take 3 sat, okay, and then and I want to. I'm not talking 3 sat. I'm talking max 3 sat.
Yeah.
I'm not trying to solve this. I'm doing max 3 sat. So I want to go up, and and now what do you want me to do?
Add deliberately contradicting terms.
Mm-hmm.
And so when you perturb, you're going to increase the cost function, increase like the yield function. Oh, somehow or another, you're saying my argument was that I had more good than bad, so now you want me to... In this specific problem,
yeah,
so just change the problem.
Well, yeah, but then... So you want me to add more bad clauses, so those can only get better.
Yeah.
And then...
And that maybe will help.
Okay, I have to think about that. Yeah, I'm a little suspicious that that's too good to be true, but I'll think about it. I don't think I can process that in real time. Okay, but I think it's an idea, but I'm suspicious. But I'll think about it. Okay. Okay. So anyway, conclusion. So this is the conclusion of my whole spiel, and then we can ask questions. The QAOA is an easy-to-implement all-purpose optimizer, which is kind of nice. It has worst-case performance guarantees. I can prove that in certain cases it must succeed with a certain probability, which does not beat the best classical algorithms. As I started to say before, performance improves with depth, meaning that every numerical experiment anyone has ever done, as you increase the depth, it just gets better and better without limit. And that's interesting because if you believe that it has to fail, then you might think that there were cases where you'd see it fail. But I don't know. Maybe we're just the sizes are just too small. But you know, we could talk about what success would mean if we got beyond a certain point. But there's no experimental. There's no when I say experimental, I mean on laptop experiments or even with bigger computers. We can analyze the random instances in the infinite size limit, and there's not any hint to, my third bullet point was theoretical. Performance can only increase with depth. I explained that before, but the fifth bullet point is that there's not an obstacle to improvement. The numerics are uniformly encouraging, and I think we need to learn more. So I think that's where I'd like to stop, but now please ask me questions about things anything so that we can establish something. Go ahead.
Yeah. I'm still not sure what is the reason that you picked the unitary circuit the way you picked it?
I'm going to repeat the question for the people in the back. The question was, why did we pick it to be the thing we picked?
Yeah, with the beta and the gamma.
I don't know. I mean, it just, I don't really know. It just seemed, well, if you look at the adiabatic algorithm, there are two ingredients. One, the adiabatic algorithm is an algorithm where you start in the ground state of a particular Hamiltonian, and then which is maybe I should say what the adiabatic algorithm is. I mean, the adiabatic algorithm is a quantum algorithm which takes advantage of the adiabatic theorem. And what it does is, the adiabatic theorem says that if you start in the ground state of a quantum system and you slowly change the Hamiltonian, very, very slowly, and now you look at any time at what the ground state is of the Hamiltonian at that time, it says that it will, you're changing the Hamiltonian, and you'll follow, and as you're changing it, you're Schrodinger evolving. So you're evolving the state with a time-dependent Hamiltonian, which is slowly changing. So the state is changing, but you also can look at the Hamiltonian at the successive time, and the adiabatic theorem says that you will stay in the ground state of the instantaneous Hamiltonian. Let me demonstrate that, okay? Imagine that my hand is a potential, and and this thing is the ground state, okay? So this is the ground state. Now I move my hand slowly, I stay in the ground state, okay? But if I go like this, I lose it. So, because I went fast. And so, if you stay in the instantaneous ground state, in this case, you got better. I improved. Right? I did better. I got a better solution. Thank you very much. But, so the adiabatic algorithm says start with a Hamiltonian whose ground state you know, and then you want to end up in the ground state of a cost function whose ground state you don't know. So what you do is you interpolate between the two, and then you, and so that time, t is a big time. So at t equals 0, you have b, and at t equals capital T, you have c. And the adiabatic thing says if you start in the ground state of b, you'll end up in the ground state of c if you go slowly enough. So what you do now is if you take b to be the sum of the sigma x's, you can start in its ground state, which is just the strings, the spins lined up in the x direction, and then you morph it into the other one, and you will, and this works if you have infinite time, which, you know, is a little inconvenient. So anyway, so in the adiabatic, you have this, and some people accuse the QAOA of being a Trotterized version of this evolution. The reason I don't accept that is because the QAOA actually can just have two parameters, e to the minus I beta b, and e to the minus I gamma c. It can be at depth 1. But I guess maybe the parameter, it sort of seemed, I don't know, you ask me why did we choose those? Maybe it's because we were thinking of the adiabatic algorithm. But I'm not sure.
There was no any other reason?
No.
Natural.
Yeah, I mean, these things we had encountered.
But here, beta and gamma are not related to this T over T, right?
Well, they would be, if I have a time-dependent Hamiltonian, and then I have an evolution, I can Trotterize it. You know what I mean by that? I can write it into discrete.
I do, but that's something to do.
Oh, you know what Trotterizing means? Trotterizing means if you have, like, you know, it follows from this. If you have it's this, e to the a is the limit as n goes to infinity of e to the a over n. Well, this looks, oh, no, I'm doing something completely stupid. No, e to the a plus b is the limit as n goes to infinity of e to the a over n, e to the b over n to the n. That's that formula. Okay, so what does that mean? That means that if you have a Hamiltonian, which is the sum of two terms, you can, and now think of n as, 20, then you can approximate it by the exponential of the first with a little coefficient, the exponential of the second with a little coefficient, and that's called the Trotter formula, and it allows you to approximate time evolution of quantum systems. Instead of evolving with this thing, which is very complicated, you can just evolve with discrete little times. Now, well, there is a relation here. Let me tell you one more thing, which is sort of amusing. You know, you could say, has anyone ever heard of bang bang? You know what bang bang is? Okay. Well, bang bang is a kind of amusing, to me, amusing thing. It says that if you have an optimization task, and it depends on a continuous parameter, and maybe there are a continuous parameter, and that continuous parameter can go between 0 and 1. And so you want to do something, and you're doing it with a continuous parameter, and you want to find the optimal path that achieves a certain result. Bang Bang says that under very general circumstances, the optimal thing to do is to set the parameter to 0 for a little bit, and then set the parameter to 1 for a little bit, and then 0. So you go, you know, bang, bang, bang. And a beautiful example of that is parking your car. Suppose that you have your steering wheel, and you wish to park your car. Now, and so your optimal, you know, you're trying to achieve something, which is getting the car in the parking space. From experience, you will notice that the optimal thing to do is to turn the steering wheel all the way to the left, and then go a little bit and turn it all the way to the right. It is not to continuously turn the steering wheel. And you can prove that from Bang Bang. So anyway, if you apply Bang Bang to this, it says that the optimal thing to do is not to continuously interpolate between these two things, but to turn one on and one off. And that's the QAOA. The only little problem is that the Bang Bang may tell you that you have to take an infinite number of things. So we can't really prove that the QAOA is better than adiabatic, because of that little caveat that it might be an infinite number of things. Fortunately, when you park the car, the Bang Bang will suffice with a fixed number of turns. But they are extreme. You go all the way to the left and all the way to the right. But anyway, so there's a relationship. You know, Bang Bang would say that it's better to run the QAOA than the adiabatic. But it doesn't apply, you know, if you just go to p equals 1, the lowest depth. And I think it's amusing that the QAOA has interesting results at the shallowest depth.
So would Bang Bang say that I want to pick better to be for pi or pi?
I hear what you're saying. I don't know. I have to think about it. Does it say that you just want an alternation of those two extreme things? I don't know. Maybe. I have to go back to it. Yeah, I don't know.
In the adiabatic evolution, the small gaps play a role.
Absolutely.
What's the analogy of
Well, yeah, great question. You see, the adiabatic algorithm, you know, when I said that the time to run the adiabatic algorithm was infinite, it will work. Actually, there is a way to quantify that, and that's the following thing. If you look as a function of time here, between 1 and capital T, you have a different Hamiltonian at each time, and that Hamiltonian has a lowest energy state and a first excited state. So let me plot those energies. This is the energy of the ground state, And this is the energy of the first excited state. I just drew a picture. The levels never cross. We could talk about why levels never cross, but levels never cross. Okay? So it turns out that the actual runtime has to be much bigger than essentially 1 over the gap squared. It depends where this is the energy gap, the smallest thing. So in the case of the adiabatic, people argued that there will be situations. Oh, I'll tell you a funny story about this in a second. There should be situations where the gap is exponentially small, so the required runtime is exponentially big. And then, so that means, so you could kind of put your eye on something in the adiabatic case and say, if the gap is too small, it has to be big, and I can find physical systems where the gap, excuse me, is very tiny, leading to the failure of the adiabatic. We have no such thing here, no such thing we can latch onto that implies this. Well, let me tell you my story about, so if your physical system has an exponentially small gap, then you have failure. So I went to Alexei Kitaev, you know who that is, the great condensed matter physicist, and I said, Alexei, let's consider a spin glass model where you have couplings, but classical couplings between spins, some generic model, and I put on a transverse magnetic field, which is what this looks like. But I just said, we have a model with classical spins, and then I put on a transverse magnetic field. It's a quantum model. I vary the magnetic field. And I said, from your experience as a condensed matter physicist, what do you think the gap is? So he said, exponentially small. So I said, why do you say that? He said, otherwise the adiabatic algorithm would work. That's what he told me.
Good argument.
That's a good argument, right? That's what he told me. Otherwise, the adiabatic algorithm would work. So, it's hard to win. That was my experience. Anyway.
So,
go ahead.
just we thank Ed.
Okay, sure.
We have 90 seconds for questions.
Yeah, 90 seconds. Good. Go ahead.
So what if you start not with a perfect superposition, but a slightly noisy superposition? Will it still work, or did you try?
I mean, what we've tried is, well, no, I've tried uniform superposition of everything with constant energy. And if you start with 1, it doesn't work. If you start with superposition of 3, it doesn't work. If you start with superposition of everything, it doesn't work. But what do you mean by noisy? Mess up the phases?
No, so you try to initialize every qubit in the superposition, but it's slightly shifted to more weight to the 0 or more weight to the 1.
I don't know. I never tried that. No. What the question is a great question. In other words, is there an analog of this for the shallow depth QAOA? I don't know. I mean, and no one has really identified that. People have seen cases, though, where the adiabatic will fail, but the QAOA will succeed. There are examples of that, where you can show that the adiabatic fails and the QAOA works. But no, I don't have, see, in the adiabatic, you could say, well, if the gap is small, you're going to fail. So let's look and see what the gap is. But then can't translate that to the QAOA, and I don't have an analogous thing that I can latch on to, which would indicate failure or success. Sure.
Being a physicist,
Yeah.
this can't be quite right for dimensional reasons. So
Oh, yeah. My dimensions are wrong. Of course. Thank you. Okay. Okay. No. You're right. No, you're right. You're right. I'll fix it. So in units where h bar is 1, and then time and energy are inverse units if h bar is 1, because delta t is h bar. So this is still not okay. So I have to put a numerator in. And the numerator is some matrix element of the time of the rate of change. I have to put in a matrix element upstairs, which involves, S is like T over T. So which involves the derivative of H with respect to S and some matrix element. So that fixes the units.
No.
No.
Now it's too good because now it's h squared divided by gap squared.
The gap is in energy. No. The gap is in energy. No,
yes.
S
This is h squared.
No, it isn't. DHDS.
Yes, because S is.
No, S is T over T. I made it dimensionless.
Oh, you made it dimensional.
I got ahead of you. Yeah. So this is an energy over an energy squared, which is a time.
Good, we got it squared. Thank you.
Thank you. All right.